First actually I want to show you where we're headed with the last assignment bit. So if you run the code I give you, you get some sort of little application. I think if you hit load right now, it automatically just loads something, but you're supposed to add a file browser kind of pop-up, which is something that exists in Swing, not like you're writing all the buttons and stuff for this. You select a directory. It creates a little scroll thing of faces to look at. Sort of painfully to me, I did not make sure the aspect ratio of the picture showed up correctly, so they're all squished, which really hurts my feelings when I look at those pictures and they're not exactly the right aspect ratio, but I decided just to roll with it for this. So if you select one of them, these are the samples according to their mouth width and mouth height here. And so if I pick different ones, the yellow dot goes to different spots. That's the one that's we're treating as the unknown. So, you know, we already know what they all are, but we're going to pretend we don't know one of them. So we pick one, and you hit classify, and it shows the nearest neighbors that are there. And then it says, it really is classified as smiling, and we decide, or it really was a smiling one, and we classified it as smiling. All right, and you pick a different one. Let's pick a different one. Here's someone. And classify, it's hard to see there, and neutral. All right, so for the most part, most of this is sort of already there. I sort of kept doing stuff and thinking like, I don't really want to make you have to do this. I don't really want to have to do this, so I just did it, right? So besides fixing the KNN code, so it actually does this kind of stuff. And again, if you already started on the fruit class, this code can move directly to the faces class without any change because they all work on distances. You need to add some way of changing the K value here. So instead of 5 being hard-coded, it will make it be like 3 or 2 or whatever you want it to be. And you need to make this be a little more exciting. So not just spit out like a little mini console here, but have some nicer way of showing what the classification was. And you need to sort of restructure the whole thing overall to make it a nicer looking application instead of just dumping stuff and hoping the layout manager helps it all work out. What else? There's something else. But it's not too much. It's really, the only hard part about this is that there's like 5 different classes here, so 5 text files, and you have to have some sense of how they all fit together. And to be honest, that's closer to what you will do as a developer, if you're going to get into development, is someone hands you a whole big project and you have to figure out how to add a feature to it, not starting from scratch all the time. So this is in some ways a good experience, right? For me to give you this stuff, and then you have to figure out how to add a few things to make it work. So the only tricky thing I'd say is in some ways is kind of flipping through these things a little bit and trying to force yourself to understand sort of how these pieces relate to each other, and then adding the few little bits that I asked you to add. And the color here relates to the classification that they know. So if it's the smiley face, it's green. If it's surprised, it's red, and neutral, it's gray.
So is there anything from the fruit one that we have to turn in?
You don't have to turn in the fruit one, but if you'd started on it, the compare to is actually the exact same code for the face, and the KNN stuff is the exact same code. You want to like not grab the whole file, just copy over 2 new things. So they added a little bit to the KNN classifier to make it work better with this GUI system. So if you already started, you just migrate your changes over, and you should be good. But you don't turn anything in for that. It's a partner project again, and there is a KNN partner group that you should add yourself to. I saw someone invented their own group, which I didn't know you could do, but don't do that. And where do you see those groups? I know where I see them under people, but if you're adding yourself to these KNN groups, you know where to find those groups? I know someone did it already, so where do you see these groups to add yourself to? Under people also? Okay. It's sort of a dumb spot for it. I don't understand it. Like very yeah, bottom of people. Yeah, okay, so any questions though? It's actually the KNN part basically that lecture on Friday kind of covered exactly what you need to do. Almost gave you the code for it, I think, basically. And then this GUI stuff is just kind of messing around and being frustrated that Java won't make the buttons go where you want them to go. That's a good thing to get frustrated with and overcome. Anything else, though? All right, so just cruise. We'll just cruise to the end here. This one's no problem for anybody. Just have fun with it, hopefully. Look, there's some secret code that tells you what to do. Part of the answer. Okay, so 1410, a lot of it is about Java syntax, tools Java gives you to solve problems, and I think that's sort of predominant in a lot of your minds. But I think, as you're working on assignments, what you're finding trouble with, of course, is getting the assignments done. And the reason you're having trouble getting the assignments done is not because you're forgetting semicolons at the end of statements, or you have to go look up what an else part of an if statement is. It's because it's hard to figure out how to map the problem you're trying to work on and the solution you have in your mind to those Java statements. So it's this problem-solving aspect that's really the hard part about all this, And so for me, it's always tough when I see struggling with just the syntax when I know the real dangers lurk below and like how do I get this thing actually solved. So we've seen a few sort of common things for problem solving. So we have these our loop patterns, our optimization loops and accumulation loops, and those are things that hopefully you start to see if there's a certain kind of problem, you can apply this solution template to that. And I think even more generally, if you have some large problem, we first looked at how to take that large problem and break it up into methods, like static methods. So I have a little static method that solves one part of the problem and another one that does another part of the problem, and I put those two together, I solve the whole problem. And then more recently, we've been looking at classes as a way of organizing these solutions, right? So there's sort of a more overarching way of thinking about your solution. I want to have something that can do these services, these methods, and has this data inside it. And those are all great ways, of course, of thinking about problem solving. And I want to look at another way of sort of thinking about problem solving today. So here's a problem that should be hopefully kind of easy for you right now. Use the loop to add numbers from 1 to n, to sum them up, okay? So I want you to actually write out the code, a little static method to add up the numbers from 1 to n. Just force yourself to go through that process. And it's a good little rehearsal for final kind of stuff. So
Handwrite it?
Handwrite it, or on your computer, whatever you want to do. But I want you to actually engage yourself, and you can talk to a neighbor about it at the same time, like work through a little partner thing here. But first of all, if you can't motivate yourself to do this or don't know how to do it, then you got some problems here. But it's good here to force yourself. Can you write a loop? Add up numbers from 1 through n. So just spend a minute. All right, does anyone want to come share their solution? Let's get 2 people maybe if they're willing to come up and write down their solution. I just want to see if they're, how you're thinking about this stuff. I got 2 pieces of chalk here. One small, one tiny. Each write on half the board. Who's going to share a solution with me? All right, come up. Someone else too. Let's get 2 people. You get the big piece of chalk. You get the small piece of chalk. Try to write it a little bit big so we can. And you can write just the inner part. You don't have to write the method if you don't want to, or you can, whatever you want to do. Sharing my pain trying to fit code on PowerPoint slides now. Kind of, make it big enough to fit, and then. So we have a static method, sum 1 to n, add numbers, both of them taking an n parameter. We have some kind of accumulation build, right? Sum. We go in a loop from 1 to n and add that variable 1, 2, 3, 4, 5 to the sum and return the sum. I take some issue with the variable name count here because it's not really counting, right? You're accumulating a sum, but that's fine. Minus 5. So hopefully most of you had some kind of thought like add 1 to sum, 2 to sum, and so on all the way to n, which is what this is kind of encoding, right? Taking a series of numbers and add into some variable that's being accumulated. But this, it's not the only way you can think of adding a sum of numbers. You could say add up the first half of the numbers, and then the second half of the numbers, and then add those two sums together, right? That's one way to think of it. But the problem here is that that's sort of complicated. It doesn't really match the way we know how to do things, like making a loop going 1, 2, 3, 4, 5. And so here the programming language, in some sense, is dictating the way we're solving the problem. It's sort of encouraging us to think about going from the beginning, going one at a time to the end, and not some sort of other form that's harder to encode possibly in a program. So what you'll find as you learn more languages is that sometimes some of the languages sort of encourage a certain style of problem solving, and you might like that style, and it might make you sort of be more productive as a developer. So here's another approach. Add n to the sum of 1 through n minus 1, right? So instead of saying add 1 to this number, add 2 to this number, I'm saying, well, the sum of all these numbers is the last number plus the sum of all the numbers before it. So that's one way of kind of thinking about this. So we can encode that something like this, int sum 1 to n, take in n, and we return n, the last number, plus the sum of all the previous numbers. Okay? So let's try to see what happens when we run this code. Do a little bit by hand here. All right, so if I say sum of 1 to n of 5, when I make this call, it enters this code here, n becomes 5, and it says return 5 plus the sum, I'm just going to call it sum instead of 1 to n here, of n minus 1, which is 4, right? Well, this becomes 4 plus the sum of numbers 1 to 3. This becomes 3 plus the sum of numbers 1 to 2. This, whoa, more stuff here. becomes 2 plus the sum of numbers 1 to 1. That becomes the 1 plus the sum, 0, 0 plus the sum, minus 1, and it never stops, right? So this code isn't quite right. And in fact, if we try to encode this, we can write it in our Java. So I'm going to do a public static int sum 1 to n, int n, return n plus sum 1 to n minus 1. And down here, I'm going to say int sum equals sum 1 to n of 5. And if I run this, let's print it out, I guess. So if I run it, we get some problems here. And it's the same problem we sort of saw on the board. So it basically says exception in main, stack overflow error. What's the stack? Anyone remember what the stack is? So there's the stack and the heap. What's the stack? It's like the stack holds basically the local variables in whatever function you're calling, right? So if I call a function, this one, n goes on the stack, and any other local variables go on the stack. If I call another function after that, those go on the stack as well. When I leave the function, they go off the stack. Here, n keeps getting put on the stack over and over again as a new variable, and eventually runs out of memory, basically. So we can't just keep adding things to the stack. Eventually it runs out. So the problem here is that if I printed out n, we would see a little bit more information about what's going on here. So, okay, we must scroll. So n went from 5, 4, 3, 2, well, okay, let's see if we can get to it. Oh, ran out of, went 5, 4, 3, 2, 1, 0, negative 1, negative 2, negative 3. N kept getting smaller and smaller, and eventually sort of crashed the computer in some sense. So when we get to some big number here, it doesn't like it anymore. So what can I do here to fix this? Yeah, we want to say there's some ending case that we know the value of. So we're trying to add 1 to n, so we can say if n equals 1, just return 1. The sum of 1 up to 1 is 1, right? And other than that, we can return the sum of the current number plus the smaller number. Now, if we had that code in there, we would have said n is 1. That whole thing would evaluate to, so this whole thing here, sum of 1, that hits the return 1 case, right? So that becomes 1. And all of a sudden now we can add 2 plus that 1. And this whole thing turns into 3. So this thing now turns into 3. And then we can add 3 plus 3 to get 6. And then 4 plus 6 is 10. And then 5 plus 10, because the sum of 4 is 10, equals 15. All right? So let me run it now. And we get that the sum of 1 to n is, for 5 is 15. So the way this works is, it says, okay, if it's 5, then it's 5 plus the sum of 1 to 4. To figure out what sum of 1 to 4 is, it calls itself and says the sum of 1 to 4 is 4 plus the sum of 1 to 3. Figure that out, sums it up. As soon as this turns into a number, it can start actually evaluating this expression and adding them all up as it sort of pops up this call stack. So when we solve problems like this, we call it solving it recursively. And I think it's a powerful way of thinking about solving problems, all right? This is not a great example. We know how to add numbers from 1 to n, and so doing it recursively sort of adds mystery rather than clarity to it. But there are problems that map very naturally into this way of thinking about things. Now, recursive methods need 2 parts. They need the base case, which is some specific answer for some simple case. Like usually, if you're adding a bunch of numbers, it's the 0 or 1, whatever it is. It's the simplest thing you can think of, and you already know the answer to it, basically. And then there's some sort of reduction step where if you have some larger case, you figure out how to break the problem into parts where you can progress towards the base case. So for example, in our 1 to n thing here, we have a base case. If n equals 1, return 1. That's the part we already know. Otherwise, there's some reduction step. Break it into what we know about the current thing plus the remaining part. And notice, since n is getting smaller here, we're making progress towards this base case. Okay? So a lot of people mess up recursion because they forget some aspect of it. Like they pass in something here that doesn't move the system towards this base case, and then it just sort of goes forever. It's like an infinite loop. Or they don't accumulate it properly. But it's sort of weird to me that we can add this up and we don't sort of have to go over all the numbers, right? We just sort of say, oh, well, we know this case, and we know how, in general, sort of how to make it add up, pick what we are plus the rest of it, and it just sort of works, right? This is related to a certain math technique for proving stuff. Anyone recognize what kind of thing this is?
Isn't that Gauss' formula? Or I guess not really.
Well, yeah, it's not. That's like.
Couldn't you use that though, technically, to?
Are you talking about like the n over 2 stuff?
Yeah. Because I did that to figure it out. But
oh, like how? Okay, so that's obviously you're looking at I mean.
you get the same answer.
If you're doing it by hand, yeah, you get that. That sort of makes a short formula for a larger problem. This still does all the work, right? It's not really doing figuring out the short form. But there's like some sort of math form, yeah.
Is it the Fibonacci sequence?
Oh no, this is not. This is adding up numbers 1 through n. I'm just saying, but there's a general math technique that maybe you've taken. I don't know, maybe you haven't, but that has this idea of a base case and a reduction step. Anybody? I know there's some like math majors in here.
Is it like Taylor expansion series where?
Okay, I just think it's a. I'm thinking about inductive proofs, or like this. So if you're running that term, inductive proofs, it's like this, where you have a base case and then you try to reason your way towards the base case. All right, go take some more math, everybody. You're all, calculus doesn't go in that direction. So 2100, you'll see that if you take 2100. So it's kind of hard to figure out what's going on, when you run this thing, right? So sum of 1 to n for 3 is 3 plus sum of 1 to n of 2. That breaks into this. You start getting values back, and you can sort of work your way up the complexity. But the computer handles all this for us. We don't have to kind of, do this bookkeeping ourselves. It'd be very complicated to figure that out. So the code is very simple, but what goes on underneath is quite complicated, right? Because how do you know what this is? Well, when you see an expression, it says, okay, do I know the value of this thing? Yes, it's like 3. Do I know the value of this thing? I get the value by calling this function and seeing what's returned. So it has to call it and return it. And when it calls that, it calls itself again another time, another time, another time. But the computer doesn't get confused like we would have a hard time writing this all out. Okay, so recursive solutions often have a very terse bit of code, but their execution paths are quite complicated. Yeah.
Do recursive methods have to always call themselves as their method?
You can have stuff that sort of bounces. I mean, at some point it has to come back to itself to be called recursion. Right. But you could have, I had a terrible example, like is even, is odd, and I said it's even if it's if the 1 minus itself is odd, right? And odd was, it's odd if 1 minus itself is even.
And you would never.
And then, well, there's a base case.
Oh,
One is
zero.
one is
Zero.
odd and 0 is even, but it would bounce back and forth to each other and get to some solution. So, but it would eventually cut back to itself. All right, let's look at another. Okay, so let's. Man, I don't want to show this, I guess. Notice there's this n parameter here. It's local to every time you call that method, a new n parameter is made. So in the course of recursing, there's going to be like 5 or 6 n's made, but they're all different. They're all in different places in the stack. Okay, so even though it has the same name, it doesn't share a value there. So keep that in mind as well. So things with recursion, you don't have the proper base case, you can get an infinite loop kind of thing. You can run out of stack space if you recurse too deeply. In other words, before you start getting an answer, it keeps going down, down, down. In general, recursive approaches can be converted to use a loop. And there's some problems. You can kind of make things that look pretty normal but have bad computational properties. So let's look at, someone mentioned the Fibonacci sequence. Fibonacci sequence is kind of a famous math sequence. It was originally developed to describe like the population of rabbits as they breed. There's 2 rabbits, and then they have offspring, and they have offspring, offspring, offspring. So the way you get the Fibonacci sequence is, to get this one, you add the 2 previous numbers. To get the next one, you add the 2 previous numbers. To get this one, you add the 2 previous numbers, this one, the 2 previous numbers, and so on, right? So it's a very simple formula. Like, we can do it by hand pretty easily. And it shows up in a lot of places. This is sort of called the golden spiral. It has applications in art. People look at the ratios of how this grows and find it sort of pleasing. It shows up in, like, seashells. If you look at nautiluses, how they grow look like this. It has all sorts of places it shows up. That's sort of mind-blowing, right? If you look at the number of branches on like flowering plants, it follows Fibonacci sequence. So anyway, that was, yeah, it's weird. It's year plus, it's like the golden ratio. So again, the Fibonacci sequence, each number is the sum of the 2 preceding numbers, and you can kind of write it like the Fibonacci sequence for n equals n minus 2 plus n minus 1. That's, how this works. What's the base case for this Fibonacci sequence? If we're trying to do this recursively, like, where do we actually know an answer?
Well, wouldn't this one be hard because Fibonacci sequences don't always work backwards? No, they work.
Well, let's say we want to know the 5th number in the Fibonacci sequence, right? So to compute that, we can compute it by knowing the 4th number and the 3rd number, but eventually we need to hit some base case. So what's the base case here?
0 and 1.
Yeah, so actually we have 2 base cases. If we want the first number, or the 0th number really is a 0, and the first number is a 1, and we can build everything up from that. This part is really the recursive step, right? If we know the base cases and we know this, notice these numbers get smaller. We go from n to n minus 2, n minus 1. And so the code for this might look something like this. Public static int Fibonacci, int n. If it's 0, return 0. If it's 1, return 1. Otherwise, return the sum of those previous Fibonaccis. All right, so let's implement that, I guess. I haven't written a static method in a while. It feels weird, right, to have that static in there. I'm just going to call it fib, takes in an int n, and if n equals 0, I'm just going to kind of keep it all on line to keep it concise here, not for any particular reason. Otherwise, return fib of n minus 2 plus fib of n minus 1. All right, so again, you write this code and you're like, how does this capture anything meaningful about these number sequences, right? But in fact, this captures everything meaningful about these number sequences. It says the first number is this, the second number is this, and any other number is this actually written down the relationship between these other numbers, right? We've actually kind of captured the essence of the Fibonacci sequence here and said any big number for n is adding up the two previous numbers. And so it actually kind of beautifully captures this, as long as you sort of, and you have to sort of, again, trust in the computer to make these things work. So I'm going to change that to a fib call, fibnum, and if I run this, 5. Well, that's not very exciting, right? So Fibonacci 5, so we have 0, 1, 1, 2, well, I'm not going to, did I get off somewhere? This is 5, but 0, 1, 2, 3, 4, 5, oh, counting from 0, okay, yeah. So this is the 0th number, the first, second, third, fourth, fifth. So fib of 5 was equal to fib of 4 plus fib of 3. And how do we know what fib of 4 was? Well, fib of 4 was equal to 2 plus 1. And 2 is equal to 1 plus 1, and so on. And that all seems pretty nice, but it gets a little complicated. So if we think about fib of 3, let's think of a real basic case. Fib of 3 is fib of 2 plus fib of 1. Fib of 2 is fib of 1 plus fib of 0. This one returns 1 because it's a base case. Fib of 0 returns 0 because it's a base case. So this whole call turns into return 1 plus 0, which is 1. So this turns into return 1 here. And then we evaluate the fib 1, and fib 1 is a base case, returns 1. So we can say this is 1 plus 1 equals 2. So Fibonacci of 3 is 2, and that's correct. Let's kind of see how many calls we have to make to compute this thing. So if I go back to Eclipse, I'm going to make a public static int count. I'm going to have a variable that hangs around that we can use to count things up. And I'm going to count how many times I come into the Fibonacci call. So how many times it recurses on itself, basically. And before I call it, I better set that to 0, make sure if I do it over and over again. And here, I'm going to say called fib count times. All right, so for fib of 3, if I run it, we get an answer of 2, and I called fib 5 times. And in fact, so fib of 3, oops, where are we? Go in here. It called it once here, twice, 3 times, 4 times. I don't know, I'm missing one somewhere here, but you can kind of see, oh, this one plus this one, I think. So 5 times. So fib of 3 is 5 times. How many times do you think fib of 4 should take? Anyone have any guess? I don't actually have any good guess, but you can guess something. You can be awesome and get it, figure it out. At least double, he says. All right, so that's a reasonable thing to think about. So let's go fib of 4. 9 times. Not quite. Fib of 5.
Double minus 1.
15. Let's go to 10. Getting a little dangerous. 20,000. This is only the 30th number in the sequence. and it calls it 2 million times. All right, so this is the danger of the recursion in some sense. We're like, hey, I know how to solve this problem, but we're not thinking very carefully about the cost of this. Why is this so expensive? It's like, well, here we're computing fib n minus 1, which computes fib n minus 2 plus some or other number. And we have to compute fib n minus 2 again here. So it's like we're branching and we're doing redundant computations all the time, that this one needs n minus 2, this one needs n minus 3, but this one eventually needs n minus 3 as well. You know, so each one is sort of recomputing itself like over and over and over and over again to get to the final. So like fib 2 in this case gets called, you know, 1 million times basically to figure out what fib 2 is in this case, because that's the bottom case of all this branching kind of thing going on here.
Wouldn't it be easier to use an array in a loop?
Easier? We're not, yeah. So there are ways to, of course you want to store, if you've already computed one of these things, you want to store it somewhere and use it again and not, not keep doing it over again. But this, you know, it's kind of sad because this elegantly portrays how this thing should compute.
So does that mean it's only storing like 2 objects in the stack at a time?
Well, the stack, of course, keeps track of, every time you recurse, there's going to be, like, here's the stack, and there's going to be the fib5 call. Right? And that's going to store an n equals 5. And then to get fib5, we're going to compute fib4. And that's going to store an n equals 4, a different n in a different location, right? In the stack. And to get fib4, we need fib3. And fib2. And then fib1, at this point, and I'm pretending this is not the branching Fibonacci kind of thing, really just sort of going down. At this point, we know what this is worth. We can evaluate what fib1 is. That's equal to 1. So we pop the stack, that 1 gets transmitted back up to here, we add those up together, we can then evaluate what this is, so it goes off the stack. So we sort of go down the stack, filling it up, and then when we get to that base case, we can start removing items, propagating back up the stack. Okay? And really it's the same kind of thing as I was trying to show here, that you sort of have to keep recursing until you can get an actual value out, and then that expression turns into a number rather than another function call. And once it has a number, it can actually return it and leave that scope and go back up to the next scope of the recursion kind of thing. All right, so I only really show the Fibonacci stuff to say 2 things. One is that the cases here are going to be more complicated than just the n minus 1 all the time, right? We can start having these branching kind of things going on. And it says, I need to evaluate this, and I need to evaluate this. To evaluate it, it recurses. But the other thing is that you can also get yourself into trouble here. So if I wanted to compute the millionth number in the Fibonacci sequence, this would be a terrible way to do it. It would take probably like lifetime or universe kind of times to compute this kind of thing, because it'd be, you know, if 30 takes 2 million times, imagine what a million numbers would take, right? It would take a lot. And in fact, you're probably better off propagating forward, like making an array list and saying, give me the last 2 values, add them up, stick them on the end of the array list. Give me the last 2 values, add them up, stick them on the end of the array list. You know, that's how you would sort of do this going forward more easily. But on the other hand, I don't mean to show you this stuff just to make recursion look bad. Recursion can help clarify how you think about problems and actually write efficient code for it. So let's say I want to write some code to look at my family tree and decide if any of my ancestors were named David, like whether I'm the first David in my sequence of ancestors or not, right? So there's me. How would I find whether any of my ancestors are David? It's not fair to just say, go and look if any of my ancestors are David, right? I don't have that stored in that kind of way. So how are ancestors like organized for somebody? What do I have to know? You know, here's me. You're talking about my ancestors. What else do I have to know? Like
Birth and death certificates.
I'll have to say parent 1. Parent 2, 3, 4, who knows, right? This is how family trees are organized. You have a person, and they have ancestors. Now, what can I say about parent 1? They have ancestors, right? And how about parent 2? They have ancestors of some kind. So, how can I solve a problem knowing if any of my ancestors are named David? Besides saying, look at all the ancestors, right? Try to break it down into some steps where I can make some progress computationally. What's a way of thinking about this? What's something I can ask that I know, like, kind of right away here? Okay, so are either of the parents David? So that's a case we can solve, sort of a base case kind of thing, right? What else can I ask then, if that's not true? If it's true, then I'm done, right? I have someone named David. What's something else I can ask then?
Are their parents named David?
Does parent 1 have an ancestor named David? All right? So I sort of know about myself and I know about my parents, but then they can ask their parents about what's going on. And then does parent 2 have an ancestor named David? All right, so one way of thinking of this, well, let's use some sort of code. Have ancestor named David. If name equals David, then I'm done. I've found it. It's true. If I don't have any ancestors, then it's false. Like if I don't have any parents, I can't have one named David. And then otherwise, ask whether parent 1 has an ancestor named David or parent 2 has an ancestor named David. And of course, the or is the important part, right? Like both don't have to be true for me to have an ancestor named David. Only one side of the family needs a David in there for this to be true. So if this returns true, then the whole thing is true. Even if this is false, if both are true, it's true. But if they're both false, it's false. And the reason it would be both false would be they run out of people to look at.
Couldn't we not call this on, this would have to be called on the first row, his first parent, because the first line would make it so it would return true because his
Oh yeah, not on myself, yeah.
So this would have to be,
I would kick it off somewhere by asking if any of my parents have.
so this would start like his parent.
Yeah. And this is inside some class, right, where there's actually like parent 1 and parent 2 as instance variables or something, right? So this is more working on in some larger scheme. But notice this is a pretty nice way of thinking about this. Rather, the other way would be like collect all the parents into some big array list, and then ask if the array list has a parent, named David. That's one way of thinking about it. But that's mapping your solution to sort of your understanding of Java, which is like lists and arrays kinds of things, right? And there's other ways of thinking about solving these problems. And this one is just ask if I have found David already, if I've run out of things to look at, and then basically propagate up the tree through recursion here. So this one would ask, yeah, is this David? Is this David? Or either these David? Or other this David? Or all those David? And it's hard to structure that in a loop, really, without other things.
Would family tree have more than just single branches from each person?
Yeah, I hardly know how family trees work. I just like, don't hire me for Ancestry.com or anything. And eventually, right, what does it mean they don't have an ancestor? It means we don't have any names left, right? We don't know who they are anymore. Or they're a worm or something like that, I guess. Or go back far enough. So, recursion is not bad. I think it can help you clarify how you think about certain kinds of problems and reach sort of nice solutions without a whole bunch of bookkeeping on your own part. Another possible application, looking through folders for a file. So you want to find grades.txt or something like that. I can ask, is it here in this folder? No? Well, is it in any subfolders that are there? No, ask in subfolders of those. And again, I could write that in some complicated way, but recursively, that's going to be pretty easy to do. Just say, does a directory have this file? Well, check all the subfolders, recurse on those, and they'll go down as far as their subfolders in the tree. We see this in stuff like programming languages. So when we talked about an expression in Java, we said, hey, an expression can be a number, or it can be an expression plus an expression, or an expression in parentheses, or the negation of an expression. And notice how expression shows up both here and in the definition of itself, right? So it's a recursive definition of expression. And so again, it helps you clarify how you think about expressions in Java if you're using it already in a language. In games, collision detection often happens recursively. So if I want to say if this thing is colliding with some other model, I would say, I don't want to check every triangle, but is the top half colliding with it or the bottom half colliding with it? And if they are, then we can kind of break it down into smaller pieces and smaller pieces until we finally get to some little pork that may be colliding. So, so far we've kind of learned arrays, linear structures, they match up well with loops, and it kind of distorts your thinking and thinking everything has to match that style. But there are a lot of other data structures that you'll see, especially in 2420, trees and graphs and heaps and things like that, that are all more branchy-like. And you really need to be able to think recursively and get this under control to be successful thinking about those data structures. So you'll be seeing a lot of this in the next course in particular, and I want to make sure you have a little jump start on that way of thinking before you head into that. All right, so I'm going to do a little more recursion on Friday. Wednesday? Yeah. On Friday. More applications.